Quantum teleportation is a process by which quantum information can be transmitted from one location to another, with the help of classical communication and previously shared quantum entanglement between the sending and receiving location. Because it depends on classical communication, which can proceed no faster than the speed of light, it cannot be used for faster than light transport or communication of classical bits. It also cannot be used to make copies of a system, as this violates the no-cloning theorem. While it has proven possible to teleport one or more qubits of information between two atoms, this has not yet been achieved between molecules or anything larger. Although the name is inspired by the teleportation commonly used in fiction, there is no relationship outside the name, because quantum teleportation concerns only the transfer of information. Quantum teleportation is not a form of transportation, but of communication. It provides a way of transporting a qubit from one location to another, without having to move a physical particle along with it. The seminal paper first expounding the idea was published by C. H. Bennett, Brassard, Crapo, Joja, Perez and W. K. Wouters in 1993. Since then, quantum teleportation was first realized with single photons and later demonstrated with various material systems such as atoms, ions, electrons and superconducting circuits. The record distance for quantum teleportation is 143 kilometers. Non-technical summary. In matters relating to quantum or classical information theory, it is convenient to work with the simplest possible unit of information, the two-state system. In classical information, this is a bit, commonly represented using 1 or 0. The quantum analog of a bit is a quantum bit, or qubit. Qubits encode a type of information, called quantum information, which differs sharply from classical information. For example, quantum information can be neither copied nor destroyed. Quantum teleportation provides a mechanism of moving a qubit from one location to another, without having to physically transport the underlying particle that a qubit is normally attached to. Much like the invention of the telegraph allowed classical bits to be transported at high speed across continents, quantum teleportation holds the promise that one day, qubits could be moved likewise. However, as of 2013, only photons and single atoms have been employed as information bearers. The movement of qubits does require the movement of things. In particular, the actual teleportation protocol requires that an entangled quantum state or Bell state be created, and its two parts shared between two locations. In essence, a certain kind of quantum channel between two sites must be established first before a qubit can be moved. Teleportation also requires a classical information link to be established, as two classical bits must be transmitted to accompany each qubit. The need for such links may, at first, seem disappointing. However, this is not unlike ordinary communications, which requires wires, radios or lasers. What's more, Bell states are most easily shared using photons from lasers, and so teleportation could be done, in principle, through open space. The quantum states of single atoms have been teleported. An atom consists of several parts: the qubits in the electronic state or electron shells surrounding the atomic nucleus, the qubits in the nucleus itself, and, finally, the electrons, protons and neutrons making up the atom. Physicists have teleported the qubits encoded in the electronic state of atoms. They have not teleported the nuclear state, nor the nucleus itself. It is therefore false to say, an atom has been teleported. It has not. The quantum state of an atom has. Thus, performing this kind of teleportation requires a stock of atoms at the receiving site, available for having qubits imprinted on them. The importance of teleporting nuclear state is unclear. Nuclear state does affect the atom, e.g., in hyperfine splitting, but whether such state would need to be teleported in some futuristic, practical application is debatable. An important aspect of quantum information theory is entanglement. measurement, which imposes statistical correlations between otherwise distinct physical systems. These correlations hold even when measurements are chosen and performed independently, out of causal contact from one another, as verified in Bell test experiments. Thus, an observation resulting from a measurement choice made at one point in spacetime seems to instantaneously affect outcomes in another region, even though light hasn't yet had time to travel the distance, a conclusion seemingly at odds with special relativity. However, such correlations can never be used to transmit in any information faster than the speed of light, a statement encapsulated in the no-communication theorem. Thus, teleportation, as a whole, can never be superluminal, as a qubit cannot be reconstructed until the accompanying classical information arrives. The proper description of quantum teleportation requires a basic mathematical toolset, which, although complex, is not out of reach of advanced high school students, and indeed becomes accessible to college students with a good grounding in finite-dimensional linear algebra. In particular, the theory of Hilbert spaces and projection matrices is heavily used. A qubit is described using a two-dimensional complex number-valued vector space. The formal manipulations given below do not make use of anything much more than that. Strictly speaking, a working knowledge of quantum mechanics is not required to understand the mathematics of quantum teleportation. Although without such acquaintance, the deeper meaning of the equations may remain quite mysterious. Protocol. The prerequisites for quantum teleportation or a qubit that is to be teleported. A conventional communication channel capable of transmitting two classical bits, and means of generating an entangled EPR pair of qubits, transporting each of these to two different locations, A and B, performing a Bell measurement on one of the EPR pair qubits, and manipulating the quantum state of the other of the pair. The protocol is then as follows. An EPR pair is generated, one qubit sent to location A, the other to B. At location A Bell measurement of the EPR pair qubit and the qubit to be teleported is performed, yielding one of four measurement outcomes, which can be encoded in two classical bits of information. Both qubits at location A are then discarded. Using the classical channel, the two bits are sent from A to B. As a result of the measurement performed at location A, the EPR pair qubit at location B is in one of four possible states. Of these four possible states, one is identical to the original quantum state, and the other three are closely related. Which of these four possibilities actually obtains is encoded in the two classical bits. Knowing this, the qubit at location B is modified in one of three ways, or not at all, to result in a qubit identical to the qubit that was chosen for teleportation. Experimental results and records. Work in 1998 verified the initial predictions, and the distance of teleportation was increased in August 2004 to 600 meters, using optical fiber. Subsequently, the record distance for quantum teleportation has been gradually increased to 16 kilometers, then to 97 kilometers, and is now 143 kilometers. Set in open-air experiments done between two of the Canary Islands. There has been a recent record set through supercooled nanowire that reached the distance of 101 kilometers. For material systems, the record distance is 21 meters. A variant of teleportation called open destination teleportation, with receivers located at multiple locations, was demonstrated in 2004 using 5-photon entanglement. Teleportation of a composite state of two single photons has also been realized. In April 2011, experimenters reported that they had demonstrated teleportation of wave packets of light up to a bandwidth of 10 MHz while preserving strongly non-classical superposition states. In August 2013, the achievement of fully deterministic quantum teleportation using a hybrid technique was reported. On 29 May 2014, scientists announced a reliable way of transferring data by quantum teleportation. Quantum teleportation of data had been done before but with highly unreliable methods. On 26 February 2015, scientists reported the first experiment teleporting multiple degrees of freedom of a quantum particle. Researchers have also successfully used quantum teleportation to transmit information between clouds of gas atoms. Notable because the clouds of gas are macroscopic atomic ensembles. Formal presentation. There are a variety of ways in which the teleportation protocol can be written mathematically. Some are very compact but abstract, and some are verbose but straightforward and concrete. The presentation below is of the latter form, verbose, but has the benefit of showing each quantum state simply and directly. Later sections review more compact notations. The teleportation protocol begins with a quantum state or qubit in Alice's possession that she wants to convey to Bob. This qubit can be written generally in bracket notation as the subscript C above is used only to distinguish this state from A and B below. The protocol requires that Alice and Bob share a maximally entangled state. This state is fixed in advance, by mutual agreement between Alice and Bob, and can be any one of the 4 Bell states shown. It does not matter which one. In the following, assume that Alice and Bob share the state. Alice obtains one of the particles in the pair, with the other going to Bob. The subscripts A and B in the entangled state refer to Alice's or Bob's particle. At this point, Alice has 2 particles, and Bob has 1 particle. In the total system, the state of these 3 particles is given by Alice will then make a local measurement in the Bell basis on the 2 particles in her possession. To make the result of her measurement clear, it is best to write the state of Alice's 2 qubits as superpositions of the Bell basis. This is done by using the following general identities, which are easily verified, and one applies these identities with A and C subscripts. The total 3-particle state of A, B and C together thus becomes the following 4-term superposition. The above is just a change of basis on Alice's part of the system. No operation has been performed and the 3 particles are still in the same total state. The actual teleportation occurs when Alice measures her 2 qubits A, C in the Bell basis. Experimentally, this measurement may be achieved via a series of laser pulses directed at the 2 particles. Given the above expression, evidently the result of Alice's measurement is that the 3-particle state would collapse to one of the following 4 states. Alice's 2 particles are now entangled to each other in one of the 4 Bell states, and the entanglement originally shared between Alice's and Bob's particles is now broken. Bob's particle takes on one of the 4 superposition states shown above. Note how Bob's qubit is now in a state that resembles the state to be teleported. The 4 possible states for Bob's qubit are unitary images of the state to be teleported. The result of Alice's Bell measurement tells her which of the above 4 states the system is in. She can now send her result to Bob through a classical channel. 2 classical bits can communicate which of the 4 results she obtained. After Bob receives the message from Alice, he will know which of the 4 states his particle is in. Using this information, he performs a unitary operation on his particle to transform it to the desired state. If Alice indicates her result is Bob knows his qubit is already in the desired state and does nothing. This amounts to the trivial unitary operation, the identity operator. If the message indicates Bob would send his qubit through the unitary quantum gate given by the Pauli matrix to recover the state. If Alice's message corresponds to Bob applies the gate to his qubit. Finally, for the remaining case, the appropriate gate is given by teleportation is thus achieved. The above-mentioned 3 gates correspond to rotations of pi radians about appropriate axes. Some remarks. After this operation, Bob's qubit will take on the state, and Alice's qubit becomes an part of an entangled state. Teleportation does not result in the copying of qubits, and hence is consistent with the no-cloning theorem. There is no transfer of matter or energy involved. Alice's particle has not been physically moved to Bob, only its state has been transferred. The term teleportation, coined by Bennett, Brassard, Crapo, Jojar, Perez and Wouters, reflects the indistinguishability of quantum mechanical particles. For every qubit teleported, Alice needs to send Bob 2 classical bits of information. These 2 classical bits do not carry complete information about the qubit being teleported. If an eavesdropper intercepts the 2 bits, she may know exactly what Bob needs to do in order to recover the desired state. However, this information is useless if she cannot interact with the entangled particle in Bob's possession. Alternative notations. There are a variety of different notations in use that describe the teleportation protocol. One common one is by using the notation of quantum gates. In the above derivation, the unitary transformation, that is the change of basis, can be written using quantum gates. Direct calculation shows that this gate is given by where H is the 1-qubit Walsh-Hadamard gate and is the controlled NOT gate. Entanglement swapping. Teleportation can be applied not just to pure states, but also mixed states. That can be regarded as the state of a single subsystem of an entangled pair. The so-called entanglement swapping is a simple and illustrative example. If Alice has a particle which is entangled with a particle owned by Bob, and Bob teleports it to Carol, then afterwards, Alice's particle is entangled with Carol's. A more symmetric way to describe the situation is the following. Alice has 1 particle, Bob 2, and Carol 1. Alice's particle and Bob's first particle are entangled, and so are Bob's second and Carol's particle. Alice, Bob 1, Bob 2, Carol, Now, if Bob does a projective measurement on his 2 particles in the Bell state basis and communicates the results to Carol, as per the teleportation scheme described above, the state of Bob's first particle can be teleported to Carol's. Although Alice and Carol never interacted with each other, the particles are now entangled. A detailed diagrammatic derivation of entanglement swapping has been given by Bob Toecker, presented in terms of categorical quantum mechanics. N-state particles. One can imagine how the teleportation scheme given above might be extended to n-state particles, i.e., particles whose states lie in the n-dimensional Hilbert space. The combined system of the 3 particles now has n-dimensional state space. To teleport, Alice makes a partial measurement on the 2 particles in her possession in some entangled basis on the dimensional subsystem. This measurement has equally probable outcomes, which are then communicated to Bob classically. Bob recovers the desired state by sending his particle through an appropriate unitary gate. Logic gate teleportation. In general, mixed states ρ may be transported, and a linear transformation omega applied during teleportation, thus allowing data processing of quantum information. This is one of the foundational building blocks of quantum information processing. This is demonstrated below. General description. A general teleportation scheme can be described as follows. 3 quantum systems are involved. System 1 is the state ρ to be teleported by Alice. Systems 2 and 3 are in a maximally entangled state omega that are distributed to Alice and Bob, respectively. The total system is then in the state A. Successful teleportation processes or LOCC quantum channel phi that satisfies where TR12 is the partial trace operation with respect systems 1 and 2, and denotes the composition of maps. This describes the channel in the Schrödinger picture. Taking adjoint maps in the Heisenberg picture, the success condition becomes for all observable O on Bob's system. The tensor factor in is while that of is. Further details. The proposed channel phi can be described more explicitly. To begin teleportation, Alice performs a local measurement on the 2 subsystems in her possession. Assume the local measurement have effects if the measurement registers the ith outcome. The overall state collapses to the tensor factor in is, while that of is. Bob then applies a corresponding local operation psi on system 3. On the combined system, this is described by where it is the identity map on the composite system. Therefore the channel phi is defined by notice phi satisfies the definition of LOCC. As stated above, the teleportation is said to be successful if, for all observable O on Bob's system, the equality holds. The left-hand side of the equation is where psi asterisk is the adjoint of psi in the Heisenberg picture. Assuming all objects are finite-dimensional, this becomes the success criterion for teleportation has the expression local explanation of the phenomenon. A local explanation of quantum teleportation is put forward by David Deutsch and Patrick Hayden, with respect to the many worlds interpretation of quantum mechanics. Their paper asserts that the 2 bits that Alice sends Bob contain locally inaccessible information, resulting in the teleportation of the quantum state. The ability of quantum information to flow through a classical channel, surviving decoherence, is